Hello there, and welcome to the Sleepy Science Society. I'm so glad you found your way here tonight. Maybe you've had a long day, or perhaps you're the kind of person who likes drifting off to deep thoughts about our cosmic home rather than counting sheep. Either way, you're in exactly the right place. Tonight's journey is about the planet beneath your feet, the air you breathe, and the water that flows through everything living. We're going to explore Earth, from its violent birth in fire and chaos to the living, breathing world we know today. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light, because tonight we're traveling through deep time across billions of years of transformation, from molten rock to blue oceans, from poisonous skies to breathable air, from barren stone to forests and fields teeming with life. This is the story of a planet that refused to stay still, that remade itself again and again, building the only world we know where minds can wonder and hands can create. Before we begin this long journey backward through time, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time, all of us connected by curiosity about the universe we inhabit. Now, let's begin. Close your eyes if you like, and imagine looking down at Earth from space. That blue and white sphere swirled with the clouds, dotted with green and brown continents, wrapped in the thinnest veil of atmosphere. It looks peaceful from up there, doesn't it? Serene, eternal. But Earth is anything but eternal in the sense of unchanging. Earth is a story of constant transformation, a planet that has been remade countless times over its long existence. And tonight, we'll follow that story from the very beginning, when there was no blue, no green, no white clouds, just darkness and dust, and the slow pull of gravity beginning to gather matter together in the cold void of space. Birth of a planet. 4.5 billion years ago, give or take about 50 million years, there was no Earth, not yet. There was only a vast, rotating cloud of gas and dust, a disc-shaped nebula swirling around a young, newly ignited star we now call the Sun. This solar nebula was the remnant of an even older stellar explosion, a supernova that scattered heavy elements across this region of space, seeding it with everything needed to build rocky worlds. In the cold darkness, particles of dust, no larger than grains of sand, drifted through the void, occasionally colliding, sometimes sticking together through electrostatic forces and the faintest whispers of gravity. These were the humblest beginnings imaginable. Dust grains clumping together, forming pebbles, pebbles gathering into rocks, rocks accumulating into boulders, then into objects the size of mountains, then small moons. These growing bodies are called planetesimals, and they wandered through the early solar system like cosmic construction materials, waiting to be assembled into something greater. The process was slow at first, taking millions of years for gravity to do its patient work. But as these objects grew larger, their gravitational pull strengthened, and the process accelerated. Larger planetesimals attracted smaller ones, sweeping up material as they orbited through the disk, growing larger still. somewhere in the region we now call the inner solar system, about 93 million miles from the young sun, one of these planetesimals grew faster than its neighbors. It sat in what would later be called the habitable zone, not too close to the sun's searing heat, not too far into the frozen outer reaches. This privileged location, combined with the particular density of material in this orbital band, allowed it to gather mass quickly. Collision by collision, impact by impact, it grew. And as it grew, something remarkable began to happen deep within its interior. The energy of all those impacts, billions of them occurring over millions of years, generated tremendous heat. Each collision converted kinetic energy into thermal energy, warming the growing protoplanet from within. But there was another source of heat, even more powerful. The early solar system was rich in radioactive isotopes, unstable atoms created in that ancient supernova and scattered through the nebula. As these radioactive elements, particularly aluminum-26 and iron-60, decayed within the growing planet, they released enormous amounts of energy. The interior temperature climbed higher and higher. Around 4.54 billion years ago, the proto-Earth reached a critical threshold. The temperature deep within became hot enough to melt iron. And this triggered one of the most important events in our planet's history, a transformation so dramatic that scientists sometimes call it the iron catastrophe, though perhaps iron revolution would be more appropriate, because it built the world we know. Iron is dense, much denser than the rocky silicate materials that made up most of the young planet's mass. When the iron melted, it began to sink, pulled by gravity toward the center. This wasn't a gentle process. Picture enormous rivers of molten metal, heated to thousands of degrees, plunging through partially molten rock, releasing even more gravitational energy as they fell. This additional heat melted more material, which allowed more differentiation, creating a runaway process that fundamentally restructured the entire planet. The heaviest materials, primarily iron and nickel, sank to form the core. Lighter materials, rich in silicon, oxygen, magnesium, and aluminum, rose toward the surface. In between, denser rocks rich in iron and magnesium settled to form the mantle. This process of differentiation happened remarkably quickly in geological terms, probably completing within just 10 million years after the proto-Earth first began to form. By 4.5 billion years ago, Earth had a layered internal structure, the basic architecture it retains to this day. The core formed in two parts, each with its own remarkable properties and crucial role in Earth's evolution. At the very center, where pressures exceed 3.5 million times atmospheric pressure at sea level and temperatures rival the surface of the sun, reaching approximately 5,000 to 7,000 degrees Celsius, the inner core solidified. Despite the extreme heat, the pressure is so immense, so utterly crushing, that iron and nickel atoms are squeezed so tightly together that they're locked into a solid crystalline structure. This metallic ball, about 1,500 miles in diameter, spins slowly at a rate slightly different from the rest of the planet, pulled by the complex interplay of magnetic and gravitational forces. It's growing incrementally larger, about a millimeter per year on average, as the planet gradually cools over geological time and more of the outer core crystallizes onto its surface. Each atom that joins the inner core releases latent heat, the energy that was keeping it liquid, and this heat helps drive the convection that powers the magnetic field. The process of inner core crystallization is not uniform or simple. As iron crystallizes, it preferentially incorporates pure iron atoms and rejects lighter elements like silicon, sulfur, and oxygen that were dissolved in the liquid metal. These lighter elements, suddenly excluded from the solid crystal, become buoyant and rise into the outer core, driving compositional convection that works alongside thermal convection. This process, operating over billions of years, has been slowly enriching the outer core in light elements while purifying the inner core. Some scientists believe this compositional convection has become the dominant force driving the geodynamo in recent geological time, possibly more important than thermal convection. Surrounding this solid inner core is the outer core, a sphere of liquid iron and nickel, about 1,400 miles thick, where temperatures are still extreme, around 4,000 to 5,000 degrees Celsius. But the pressure is lower, insufficient to force the metal into a solid state. Here, iron and nickel remain liquid, flowing in complex patterns driven by Earth's rotation and by convection currents as heat escapes from the inner core and as light elements released by inner core crystallization rise upward. The flow patterns are extraordinarily complex, with eddies and currents at many different scales, from planet-spanning flows that take decades or centuries to complete a cycle, down to smaller turbulent structures. This flowing, electrically conductive liquid metal generates Earth's magnetic field through a process called the geodynamo, one of the most remarkable self-sustaining systems in nature. The process works through an elegant feedback loop. The flowing liquid iron, being an electrical conductor, generates electric currents as it moves through existing magnetic fields. These electric currents, in turn, generate new magnetic fields. If the flow pattern has the right geometry, the new magnetic field reinforces and sustains the existing field, creating a self-sustaining dynamo that converts kinetic energy from the flow into magnetic energy. This process has been running continuously for at least 3.5 billion years, possibly much longer, though the magnetic field has reversed its polarity hundreds of times, with north and south magnetic poles swapping positions in events that take several thousand years to complete. The magnetic field extends far beyond Earth's surface, creating the magnetosphere, an invisible bubble that extends tens of thousands of miles into space on the sunward side and stretches into a long tail on the nightward side, distorted by the pressure of the solar wind. This magnetic shield is crucial for life because it deflects most of the charged particles streaming out from the sun in the solar wind. Without this protection, the solar wind would gradually strip away Earth's atmosphere, eroding it over millions of years, as appears to have happened on Mars, after its magnetic field died billions of ago. The magnetosphere also creates beautiful auroras when some solar wind particles follow magnetic field lines down into the upper atmosphere near the poles, where they collide with gas molecules and cause them to emit light, painting the polar skies with shimmering curtains of green and red and purple. Above the core lies the mantle, a layer of hot, dense rock about 1,800 miles thick, making up about 84% of Earth's volume and roughly 2/3 of its mass. The mantle is composed primarily of silicate minerals rich in magnesium and iron, particularly minerals from the olivine family in the upper regions and various high-pressure forms of minerals deeper down. Though solid, capable of transmitting seismic waves as a solid does, the mantle behaves over geological time like an extremely viscous fluid, flowing in enormous convection currents that drive plate tectonics at the surface. This apparent contradiction, solid yet flowing, is possible because rock at high temperature and pressure can deform plastically over long timescales, even though it responds elastically to the rapid vibrations of earthquake waves. The mantle isn't uniform. It's divided into several distinct regions based on depth, temperature, pressure, and composition. The lower mantle, extending from the core mantle boundary at about 1,800 miles deep up to about 400 miles below the surface, is the largest region. Here, the dominant mineral is a form of magnesium silicate called bridgmanite, a dense mineral that can only exist under the extreme pressures found at these depths. Scientists believe that bridgmanite, together with other high-pressure minerals, makes up about 70 to 80% of the lower mantle's volume. The lower mantle convects slowly, with hot material rising from near the core over tens of millions of years, spreading laterally when it reaches shallower depths, cooling and eventually sinking back down in what are called subducting slabs, the remains of oceanic plates that have descended from the surface. Some regions of the lower mantle appear to be accumulating material over time. Seismic studies have revealed two enormous blobs of material sitting on the core mantle boundary, one beneath Africa and one beneath the Pacific Ocean. These structures, called large, low shear velocity provinces, or superplumes, are each as large as continents and thousands of miles thick. They may be accumulations of subducted oceanic crust that has sunk to the bottom of the mantle, or they may be compositionally distinct material left over from Earth's early differentiation, or possibly both. These superplumes appear to be anchoring points for mantle plumes, narrow columns of hot rock that rise through the mantle and feed volcanic hotspots at the surface like Hawaii and Iceland. Above the lower mantle lies the transition zone, a layer about 150 miles thick where minerals undergo phase transitions, rearranging their crystal structures to more compact forms that can withstand the increasing pressure found at shallower depths. These phase transitions occur at specific depths and create distinct boundaries that seismic waves reflect off, allowing geophysicists to map the internal structure of Earth. The most important transition occurs at about 250 miles depth, where olivine transforms into a denser mineral structure called wadsleyite, and then at about 320 miles depth, wadsleyite transforms into an even denser structure called ringwoodite. Finally, at the top of the transition zone around 400 miles deep, ringwoodite breaks down into perovskite and magnesiowustite, denser still. These transitions affect how material moves through the mantle and may influence how water is transported into the deep interior, since some of these high-pressure minerals can incorporate water into their crystal structures. The upper mantle, from about 400 miles deep to just a few tens of miles below the surface, is where the action really begins in terms of plate tectonics and volcanic activity. This region contains a zone called the asthenosphere, named from the Greek word asthenes, meaning weak, because it's particularly soft and ductile compared to the rock above and below. The asthenosphere, lying roughly between 50 and 120 miles deep depending on location, is hot enough that a small percentage of the rock, perhaps 1 to 5%, is partially molten. This partial melt doesn't form large pockets of liquid magma, but rather exists as thin films between mineral grains, making the rock flow more easily. Somewhat like how a small amount of water makes sand flow more easily than dry sand. This weak, ductile layer is crucial because it allows the rigid plates above to move independently, sliding slowly over the flowing asthenosphere like ships floating on a very thick, very slow ocean. The boundary between the lithosphere and asthenosphere isn't sharp, but gradual, a transition zone where rock becomes progressively softer and more ductile with depth. This boundary is defined not by composition, which is similar in both layers, but by temperature. The asthenosphere is hot enough to partially melt, while the lithosphere above is cool enough to remain rigid. The depth of this boundary varies depending on location and tectonic setting. Under cold ocean floor far from plate boundaries, the lithosphere can be over 100 miles thick. Under mid-ocean ridges where hot mantle rises close to the surface, it might be only a few miles thick. Under continents, it averages about 100 to 150 miles thick, but this can vary considerably. This variation in lithosphere thickness affects how plates move and interact, influencing everything from earthquake patterns to the locations of volcanoes. At the very top, thin as the skin on an apple when compared to the whole planet, is the crust. In those earliest days, as the planet's surface cooled, minerals with the highest melting points crystallized first, forming thin, unstable slabs of primitive crust. These early crustal fragments were probably similar to modern oceanic crust, dark and rich in magnesium and iron, what geologists call mafic composition. They floated on the still molten mantle like icebergs on water, constantly being recycled back into the interior as new heat and impact events melted them away. But Earth's formation wasn't finished. The young planet, still glowing with internal heat, its surface pocked with craters, wrapped in a thin atmosphere of escaped gases, was about to experience its most dramatic transformation yet. Somewhere else in the inner solar system, another large planetesimal, perhaps as big as Mars and with about 10% of Earth's mass, had formed. Its orbit was unstable, perturbed by the gravitational pull of the other growing planets. And one day, about 30 to 50 million years after Earth first began to coalesce, this Mars-sized body, which scientists call Theia, was pulled into a collision course with the young Earth. The impact was cataclysmic beyond imagination. Theia struck Earth at an oblique angle, not head-on, but at about 45 degrees, hitting with enough force to vaporize both bodies' outer layers. The impact generated temperatures of tens of thousands of degrees. It liquefied both planets' mantles and sent enormous quantities of vaporized rock spraying into space. Much of Theia's iron core merged with Earth's, sinking to the center and possibly contributing to the distinctive chemical signatures scientists detect in Earth's deep interior today. but a significant portion of both planets' mantles, blown into space by the impact's violence, didn't escape entirely. Instead, it was captured by Earth's gravity, forming a disk of molten and vaporized rock orbiting the newly combined planet. Over the next few thousand years, this disk of debris cooled and condensed, the particles colliding and sticking together, gradually accumulating into a single large body orbiting Earth. This became our moon. The evidence for this giant impact hypothesis is strong. Moon rocks brought back by Apollo astronauts have nearly identical isotopic compositions to Earth rocks, suggesting they formed from the same material. The moon has little to no iron core, consistent with being formed from mantle material, and computer simulations of such an impact produce a moon-sized body in the right orbit with the right properties. This collision had profound consequences for Earth. It added mass to our planet and likely stripped away much of any earlier atmosphere. It set Earth spinning faster, giving it a day that lasted perhaps just 5 hours. It tilted Earth's axis to its current 23.5-degree angle, creating the seasons that would later help drive climate diversity. And it gave Earth a large moon, which stabilizes the planet's axial tilt and creates ocean tides that may have been crucial for the later evolution of life. From violence came the foundation for everything that would follow. The journey from that first dust grain to a fully formed differentiated planet with oceans and atmosphere and the potential for life took perhaps 100 to 200 million years, a remarkably short time in cosmic terms. Yet in that brief window, so much happened. Matter organized itself from chaos. Gravity sorted materials by density. Heat melted and reformed rock. Volatile elements escaped to form an atmosphere. Water condensed into oceans. And somewhere in those warm oceans or volcanic springs or tidal pools, chemistry crossed the threshold into biology, though exactly when and how remains one of science's greatest mysteries. What makes Earth's story even more remarkable is how contingent it all was. A slightly different orbit, and Earth might have been too hot or too cold for liquid water. A smaller size, and Earth might have cooled too quickly, losing its magnetic field and atmosphere like Mars. A larger size, and it might have retained too much hydrogen and helium from the nebula, becoming more like Neptune. If the moon-forming impact had been more direct or more oblique, Earth and the moon might both have been destroyed, or Earth might have been left without the stabilizing influence of a large moon. If water hadn't been delivered in sufficient quantities, Earth might be dry like Venus. If radioactive elements had been less abundant, Earth's interior might have cooled faster, plate tectonics might never have started, and the carbon cycle might never have regulated climate effectively. We're still learning about how common Earth-like planets are in the universe. We've discovered thousands of exoplanets orbiting other stars, and we're beginning to find rocky planets in their stars' habitable zones where liquid water could exist. But we don't yet know how many of these planets have the right combination of size, composition, orbit, moon, plate tectonics, magnetic field, and other factors that made Earth not just habitable but actually inhabited. Earth might be one of billions of similar worlds. Or it might be rare, a fortunate accident in a universe where life is uncommon, time and continued exploration will tell. But either way, the story of Earth from dust to life is our story. The story of the only home we've ever known, and the foundation for everything that followed. The Hellish beginning. The Hadean Eon. The first eon of Earth's history is called the Hadean, named after Hades, the Greek underworld, and it's an appropriate name for a time that was truly hellish. The Hadean spans from Earth's formation at about 4.54 billion years ago to approximately 4 billion years ago, though some geologists extend it to 3.8 billion years ago, marking the transition to the Archean Eon. We have very few rocks from this time, which makes understanding the Hadean challenging. The oldest rocks found on the Earth date to about 4 billion years ago, from the Nouveau-Vuagitupu greenstone belt in Quebec, Canada. But we have something even older, tiny crystals of a mineral called zircon, remarkably durable and resistant to heat and chemical weathering, found in younger rocks in Western Australia. These zircons date to about 4.4 billion years ago, and they carry secrets about Earth's earliest days. After the moon-forming impact, Earth was a very different place than the world we know. The surface was likely covered by a global magma ocean, an entire planet-wide sea of molten rock heated to temperatures exceeding 1200 degrees Celsius. The atmosphere above this infernal sea was thick with vaporized rock, carbon dioxide, nitrogen, and water vapor, all outgassed from the interior. There was no solid ground anywhere, no oceans, no life, nothing but heat and violence and the slow work of cooling. But cool it did, gradually, over millions of years. Heat radiated into space. The magma ocean began to crystallize, with the highest melting point minerals solidifying first. These minerals, denser than the remaining liquid, sank, while lighter minerals floated toward the surface. This process, called fractional crystallization, further differentiated the composition of the crust and mantle. Eventually, perhaps after just a few million years, a thin, solid crust formed across the surface, though it remained unstable, constantly being remelted and recycled by ongoing volcanic activity and the continued bombardment of material from space. Because the Hadean Earth was still sweeping up the remaining debris in its orbital path, impacts continued. The late heavy bombardment, a period of intense meteorite and asteroid impacts, occurred from about 4.1 to 3.8 billion years ago. Evidence from the Moon's heavily cratered surface, which preserves a record of these impacts that has been erased from Earth by geological activity, suggests that the inner solar system was subjected to a storm of impactors during this time. Some of these impacts were enormous, large enough to vaporize any oceans that might have formed and sterilize the surface. Yet, between these catastrophic collisions, Earth was trying to settle into a more stable state. Those ancient zircon crystals from 4.4 billion years ago tell a surprising story. Their chemical composition suggests they formed in the presence of liquid water. This means that despite the violence of the Hadean, despite the continuing impacts and volcanic activity, Earth had cooled enough for water to condense and persist on the surface, at least temporarily, within just 150 million years of its formation. where did this water come from? Some was probably trapped in the minerals that formed Earth, released gradually by volcanism as the planet's interior heated and melted. But much of it likely arrived from space, delivered by water-rich asteroids and comets that impacted the surface during the heavy bombardment. Each impact that didn't completely vaporize the surface left behind some of its water, gradually accumulating into pools, lakes, and eventually oceans. By the end of the Hadean, around 4 billion years ago, Earth had transformed from a ball of molten rock into something approaching a recognizable planet. It had a solid crust, though thinner and more unstable than today's. It had oceans, though perhaps not as deep or extensive as modern ones, and certainly more acidic, filled with dissolved minerals and gases from volcanic activity. It had an atmosphere, though one that would be utterly toxic to modern life, lacking oxygen and dominated by carbon dioxide, nitrogen, water vapor, and various sulfur compounds. The surface temperature was likely much higher than today, possibly 40 to 80 degrees Celsius on average, heated by residual internal warmth and a greenhouse effect from all that carbon dioxide. The sky would have been orange or reddish, tinted by all that volcanic haze and the lack of oxygen to scatter blue light. The sun, younger and less luminous than today, would have appeared slightly dimmer in that alien sky. But the moon, much closer than it is now, would have loomed enormous on the horizon, its face scarred and bright, raising tremendous tides in those early oceans. This was Earth at the transition from Hadean to Archean, a world hostile to almost anything we would recognize as life, yet a world that was, in subtle ways, becoming more hospitable. The bombardment was slowing. The crust was thickening and stabilizing. Water was accumulating. And, somewhere in those warm, mineral-rich waters, or perhaps in hydrothermal vents on the ocean floor, or in protected tidal pools along primordial shorelines, chemistry was experimenting with complexity. The stage was being set for the next great transformation. Building blocks, Earth's interior architecture. Understanding Earth's interior and how it works required centuries of scientific detective work. For most of human history, we had no idea what lay beneath our feet. Ancient philosophers speculated, sometimes imagining hollow spaces, underground oceans, or realms of fire. It wasn't until the late 19th and early 20th centuries that scientists developed the tools to actually probe Earth's interior. The breakthrough came from studying earthquakes. When an earthquake occurs, it generates seismic waves that travel through Earth's interior, and these waves behave differently depending on what materials they pass through. By carefully timing when seismic waves from earthquakes arrive at seismograph stations around the world, scientists could work backward to figure out what the waves must have traveled through. Different types of seismic waves revealed different things. Primary waves, or P waves, are compression waves that can travel through both solid rock and liquid. Secondary waves, or S waves, are shear waves that can only travel through solid material. When scientists noticed that S waves from earthquakes didn't reach certain parts of Earth's surface opposite from the earthquake's location, they realized these waves must be blocked by a liquid layer, revealing the liquid outer core. The way P waves bounced off internal boundaries revealed the depths of transitions between different layers. Subtle changes in waves' speed revealed temperature and composition variations. Over decades of patient work, seismologists mapped out Earth's internal structure in remarkable detail, creating a three-dimensional picture of our planet's interior without ever drilling more than a few miles into it. The deepest hole ever drilled by humans is the Kola Super Deep borehole in Russia, which reached about 7.5 miles deep, barely scratching the surface in planetary terms. We've never directly sampled the mantle, let alone the core. Everything we know about Earth's deep interior comes from indirect evidence: seismic waves, magnetic field measurements, laboratory experiments on materials at high pressure and temperature, computer simulations, studies of meteorites that represent the primordial material from which planets formed, and analysis of rocks that formed deep in the mantle and were later brought to the surface by volcanic eruptions. This is science at its best, piecing together a comprehensive understanding of something we can never directly observe. Building models that make predictions we can test, constantly refining our picture as new evidence emerges. To understand how Earth works, to grasp how it creates mountains and moves continents, how it generates a magnetic field and recycles its surface, we need to understand its internal structure. Earth is not a uniform ball of rock. It's a complex, layered system, each layer with different properties, different compositions, different states of matter, all working together in an intricate dance that has shaped our planet's surface and atmosphere for billions of years. At the very heart, about 4,000 miles below your feet if you could drill straight down, lies the inner core. This solid sphere of iron and nickel, about 1,500 miles in diameter, exists under conditions so extreme they're difficult to comprehend. The pressure is approximately 3.6 million atmospheres. To put that in perspective, it's the weight of 3 million Earths pressing down on every square inch. The temperature is estimated at about 5,000 to 7,000 degrees Celsius, as hot as the surface of the sun. Under normal pressure, iron would melt at these temperatures, but the immense pressure deep within Earth squeezes the atoms so tightly together that they're locked into a solid crystalline structure despite the heat. The inner core isn't static. It's growing slowly, about a millimeter per year, as heat gradually escapes from Earth's interior, and more of the outer core crystallizes onto its surface. This growth releases latent heat and light elements that were dissolved in the liquid iron, driving convection in the outer core above. The inner core also rotates slightly faster than the rest of the planet, spinning independently, pulled by magnetic and gravitational forces. It's a world within a world, hidden beyond any possibility of direct observation, known to us only through the behavior of seismic waves that pass through it during earthquakes. Surrounding the inner core is the outer core, a layer of liquid iron and nickel about 1,400 miles thick. Here, temperatures are still extreme, around 4,000 to 5,000 degrees Celsius, but the pressure is lower, allowing the metal to remain molten. This liquid metal isn't sitting still. It's in constant motion, stirred by convection as heat from the inner core rises and cooler material from above sinks. Earth's rotation adds another layer of complexity, causing the flowing metal to spiral and twist, creating complex three-dimensional flow patterns. This motion of electrically conductive liquid metal is what generates Earth's magnetic field. The process, called the geodynamo, works like this. As the liquid iron flows, it carries electric currents. These currents generate magnetic fields. The magnetic fields, in turn, influence the motion of the charged, flowing metal. This creates a self-sustaining feedback loop, a dynamo that has been running for over 3 billion years, possibly much longer. The magnetic field extends far beyond Earth's surface, creating the magnetosphere, an invisible bubble that deflects most of the charged particles streaming out from the sun in the solar. Wind. Without this magnetic shield, the solar wind would gradually strip away Earth's atmosphere, as appears to have happened on Mars, which lost its magnetic field billions of years ago. The mantle lies above the core, separated from it by a distinct boundary where liquid iron meets solid rock. This boundary, called the core-mantle boundary, is a region of extreme conditions where temperatures change dramatically over short distances, and where material from the lower mantle may interact chemically with the outer core. The mantle itself is divided into several layers based on their physical properties. The lower mantle extends from the core mantle boundary up to a depth of about 400 miles below the surface. It's composed of dense silicate minerals that exist only under the extreme pressures found at these depths, particularly a form of the mineral perovskite that can only exist when squeezed by the weight of the entire mantle above. Despite being solid, the lower mantle flows over geological time, convecting slowly, with hot material rising from near the core and cooler material sinking from above. This convection is the engine that drives plate tectonics at the surface. Above the lower mantle lies the transition zone, a layer about 150 miles thick where minerals undergo phase transitions, rearranging their crystal structures to more compact forms that can withstand the increasing pressure. These phase transitions affect how seismic waves pass through this region and may influence how material moves through the mantle. The upper mantle, from about 400 miles deep to just a few tens of miles below the surface, is where the action really begins in terms of plate tectonics. This region contains a zone called the asthenosphere, from the Greek word for weak, because it's particularly soft and ductile. The asthenosphere, lying roughly between 50 and 120 miles deep, is hot enough that a small percentage of the rock is partially molten, making it flow more easily than the rock above or below. This weak layer allows the rigid plates above to move, sliding slowly over the flowing asthenosphere like rafts on a very thick, very slow river. The crust and the uppermost part of the mantle together form the lithosphere, from the Greek for rock sphere. The lithosphere is rigid and brittle, broken into the tectonic plates that cover Earth's surface. These plates are constantly moving, driven by the convection in the mantle below, though they move incredibly slowly, just a few centimeters per year, about the rate your fingernails grow. Yet, over millions of years, this slow motion accomplishes extraordinary things, building mountain ranges, opening ocean basins, recycling crust back into the mantle. There are two types of crust, fundamentally different in composition and structure. Oceanic crust is thin, averaging about 4 miles thick, dark in color, and dense, composed primarily of basalt and gabbro, rocks rich in magnesium and iron. It forms at mid-ocean ridges where tectonic plates pull apart and magma wells up from the mantle below, solidifying as it cools in contact with seawater. Oceanic crust is young in geological terms, nowhere older than about 200 million years, because it's constantly being created at ridges and destroyed at subduction zones where it plunges back into the mantle. Continental crust is fundamentally different. It's much thicker, averaging about 25 miles, but reaching up to 45 miles beneath major mountain ranges. It's lighter in both color and density, composed primarily of granite and related rocks rich in silicon and aluminum. This lower density allows continental crust to float higher on the mantle, which is why continents stand above sea level while ocean basins are low. Continental crust is also ancient, with some portions dating back nearly 4 billion years. It's less easily destroyed than oceanic crust because its low density makes it resist subduction. Instead of being recycled into the mantle, continental material tends to persist at the surface, accumulating and growing over geological time through volcanic activity, the accretion of island arcs, and the compression and metamorphism of sediments. This layered structure, from the solid inner core through the liquid outer core, through the solid but flowing mantle, to the rigid crust broken into moving plates, is not just interesting architecture. It's a dynamic system that makes Earth unique in our solar system. The combination of internal heat-driving convection, a liquid iron core generating a magnetic field, and a mobile surface constantly renewing itself creates a planet that stays geologically alive billions of years after its formation. And, as we'll see, this geological activity isn't just interesting in its own right. It has been absolutely crucial for the development and maintenance of life. This remarkable architecture didn't form instantly. It evolved over Earth's first few hundred million years through processes we are still working to understand fully. The differentiation that separated core from mantle happened early and fast, within about 10 million years of Earth's formation, driven by the immense heat generated from impacts and radioactive decay. But the crust took longer to stabilize. Early attempts at forming solid crust were repeatedly frustrated by continued bombardment and internal heat. Each major impact could remelt large portions of any crust that had formed, resetting the process. The magma ocean that covered early Earth gradually crystallized from the bottom up as heat radiated into space. But this was a slow process, taking perhaps tens of millions of years. The formation of continental crust is particularly mysterious because continents require a specific set of conditions to form. Unlike oceanic crust, which forms directly from mantle melting at mid-ocean ridges, continental crust forms through more complex processes involving multiple stages of melting and differentiation. One important mechanism is subduction, where oceanic plates descend into the mantle, partly melt, and generate magmas that are richer in light elements than the original oceanic crust. These magmas rise and solidify to form the beginnings of the continental material. Over time, through repeated cycles of melting, eruption, weathering, sedimentation, and metamorphism, this material becomes even more enriched in the lightest elements, particularly silicon and aluminum, creating true continental crust. But subduction requires plate tectonics, and plate tectonics requires a cool enough mantle that a rigid lithosphere can form and break into plates. Early Earth, with its much hotter interior, may not have had the right conditions for plate tectonics immediately. Some scientists think early Earth had a different tectonic style, sometimes called stagnant lid or sluggish lid tectonics, where the lithosphere was either immobile or moved much more slowly than today. The transition to modern plate tectonics may have occurred gradually as Earth cooled, perhaps between 3 and 2.5 billion years ago, though this timing is hotly debated. What isn't debated is that once plate tectonics got started, it transformed Earth. It created continents where there were none before. It established the carbon cycle that regulates climate. It concentrated ore deposits that would later be crucial for technological civilization. It created diverse environments that drove biological evolution. And, as we'll explore shortly, it may have been essential for oxygenating the atmosphere, the transformation that made complex life possible. The internal heat that drives all this activity comes from two main sources. Some is primordial heat, energy left over from Earth's formation, from all those impacts that assembled the planet, from the gravitational energy released when heavy metals sank to form the core. This heat is slowly leaking away, radiating into space, cooling the planet gradually. But some heat is continuously generated by radioactive decay. Elements like uranium-238, uranium-235, thorium-232, and potassium-40, scattered through Earth's interior, decay slowly, releasing energy as their atomic nuclei break apart. These radioactive heat sources have been powering Earth's internal activity for billions of years, and will continue for billions more, though they're gradually declining as the radioactive elements decay away. Scientists estimate that about half of Earth's current heat flow, the heat escaping from the interior to the surface, comes from radioactive decay, with the other half being primordial heat left over from formation. This means Earth is slowly cooling over geological time, losing about 100 degrees Celsius every billion years on average. This gradual cooling is changing how the planet works. The mantle is becoming slightly more viscous, convection is slowing slightly, and the inner core is growing as more of the outer core crystallizes. Eventually, billions of years in the future, Earth will cool enough that the outer core solidifies, the magnetic field dies, and plate tectonics grinds to a halt, as has already happened on smaller planets like Mars. But that's so far in the future that it's scarcely worth worrying about. For now, for the next few billion years at least, Earth remains geologically alive, its interior churning, its surface active, its magnetic field protecting life from space radiation. The restless surface. Plate tectonics. There's something remarkable happening beneath your feet, so slow you'll never feel it, yet so powerful it builds mountains, triggers earthquakes, and reshapes entire continents. The ground feels solid, permanent, eternal. But it's not. It's moving, drifting across the surface of the planet, has been moving for billions of years, and will continue moving for billions more. This is plate tectonics, perhaps Earth's most important geological feature, and possibly the key to why our planet supports life when others don't. The theory of plate tectonics is relatively young in scientific terms. For most of human history, people assumed the continents were fixed in place, had always been where they are now, would always remain there. But in the early 20th century, a German meteorologist named Alfred Wegener noticed something curious. The coastlines of South America and Africa seemed to fit together like puzzle pieces. The fossils found on both sides of the Atlantic matched. The rock types and geological structures aligned. Wegener proposed that the continents had once been joined together in a single supercontinent, which he called Pangaea, and had since drifted apart. The scientific community initially rejected Wegener's idea, partly because he couldn't explain what force could possibly push continents through solid ocean floor. It wasn't until the 1960s when oceanographers mapped the seafloor and discovered mid-ocean ridges and patterns in the Earth's magnetic field frozen into oceanic rocks that the mechanism became clear. The continents weren't plowing through the ocean floor. Both continents and ocean floor were part of larger rigid plates, and these plates were moving together as units, driven by convection in the mantle below. Here's how it works. Deep in the mantle, heat from the decay of radioactive elements and the gradual cooling of the core warms the rock. Warm rock is less dense than cool rock, so it rises slowly over millions of years, moving upward through the mantle like a lava lamp in ultra-slow motion. When this hot rock reaches the base of the lithosphere, it spreads sideways, cooling as it goes, then eventually sinks back down to complete the convection cell. This flowing rock drags the rigid plates above with it, pulling them apart in some places, pushing them together in others. Where plates pull apart, new crust forms. The most dramatic examples are mid-ocean ridges, underwater mountain ranges that run like seams through all the ocean basins, extending for over 40,000 miles total. At these ridges, the lithosphere is being stretched and torn. Magma from the mantle below rises to fill the gap, erupting as lava on the seafloor and solidifying to form new oceanic crust. This process, called seafloor spreading, creates new crust symmetrically on both sides of the ridge, pushing the older crust away. As the magma solidifies, iron-rich minerals in it align with Earth's magnetic field, and when Earth's magnetic field reverses, as it does irregularly every few 100,000 years, the new rocks record this reversal. The result is a pattern of magnetic stripes in the ocean floor, symmetric on both sides of the ridge, providing a clear record of seafloor spreading. Where plates collide, one of several things can happen depending on the types of crust involved. When two oceanic plates converge, the older, cooler, denser plate typically sinks beneath the younger one in a process called subduction. As the descending plate plunges into the mantle, reaching depths of several hundred miles, it carries with it water and other volatiles that were absorbed into its minerals when it was at the surface. As the plate heats up in the mantle, this water is released, lowering the melting point of the rock above and causing it to partially melt. This molten rock, less dense than its surroundings, rises toward the surface, erupting as volcanoes that form curved chains of volcanic islands called island arcs. The Japanese islands, the Aleutians, the Lesser Antilles in the Caribbean, all formed this way. When an oceanic plate collides with a continental plate, the dense oceanic plate subducts beneath the lighter continental crust. Again, water released from the descending plate causes melting in the mantle, but this time the rising magma must pass through thick continental crust on its way to the surface. As it rises, it melts and incorporates some of this continental material, changing its composition. The volcanoes that result tend to be explosive and dangerous, forming chains along the edge of the continent. The Andes Mountains in South America formed this way, as the Nazca Plate subducts beneath the South American Plate. The Cascade Range in the Pacific Northwest, home to volcanoes like Mount St. Helens and Mount Rainier, marks where the Juan de Fuca Plate descends beneath North America. When two continental plates collide, something different happens because neither wants to subduct. Continental crust is too light, too buoyant to be forced down into the mantle easily. Instead, when continents collide, they crumple, folding and stacking like a slow-motion car crash, pushing up enormous mountain ranges. The Himalayas, the highest mountains on Earth, formed when the Indian subcontinent, riding on its own plate, crashed into Asia about 50 million years ago. The collision continues today, with India pushing northward at about 2 inches per year, making the Himalayas still growing, still rising, though erosion wears them down at almost the same rate. Plate boundaries aren't always colliding or diverging. Some slide past each other horizontally in what's called a transform boundary. The San Andreas Fault in California is the most famous example, where the Pacific Plate slides northward past the North American Plate. These boundaries don't create or destroy crust, but they do generate earthquakes, sometimes powerful ones, as the plates grind past each other, occasionally getting stuck and then lurching forward suddenly when the accumulated stress overcomes friction. The importance of plate tectonics goes far beyond just explaining earthquakes and volcanoes. It's a planetary recycling system. Oceanic crust, created at ridges and destroyed at subduction zones, has an average lifespan of only about 100 million years before it's recycled back into the mantle. This means Earth's entire ocean floor is replaced roughly every 100 to 200 million years. Continental crust, though more permanent, also gets reworked through erosion, sedimentation, and metamorphism. Sediments eroded from land are carried to the ocean, deposited on continental margins. And then, when plates collide, these sediments are scraped off, compressed, heated, and incorporated into mountain ranges. This recycling is crucial for maintaining Earth's climate and habitability over geological time. Carbon dioxide, released into the atmosphere by volcanism, dissolves in rain to form weak carbonic acid. This acid weathers rocks, breaking them down chemically. The dissolved minerals, including calcium, are carried by rivers to the ocean, where marine organisms use them to build shells and skeletons of calcium carbonate. When these organisms die, their shells sink to the seafloor, forming limestone. Over millions of years, thick layers of limestone accumulate. When this limestone-rich oceanic crust eventually subducts, the limestone melts in the mantle and releases its carbon dioxide, which returns to the atmosphere through volcanism, completing the cycle. This carbon cycle, driven by plate tectonics, acts as a planetary thermostat. When Earth is warm, there's more evaporation, more rain, more weathering, more carbon dioxide removed from the atmosphere, which cools the planet. When Earth is cool, there's less weathering, but volcanism continues, so carbon dioxide builds up, warming the planet. This negative feedback mechanism has kept Earth's surface temperature within the range where liquid water can exist for most of the planet's history, despite the sun growing steadily brighter over billions of years. The timing of when plate tectonics started is still debated among geologists. Some evidence suggests it began very early, perhaps as far back as 4 billion years ago. Other evidence suggests it started later, possibly around 3 billion years ago or even more recently. What's clear is that whenever it started, it fundamentally changed Earth's evolution. And, as we'll see in the next section, the connection between plate tectonics and the development of Earth's atmosphere, particularly the rise of oxygen, may be one of the most important factors in making Earth a living world. Atmosphere's evolution. From poison to paradise. Take a deep breath. Feel that air filling your lungs. 21% oxygen, 78% nitrogen, traces of argon and carbon dioxide and other gases. It feels natural, inevitable, but that air is anything but inevitable. It's the result of billions of years of geological and biological evolution, a transformation so profound that if you could travel back in time 3 billion years, that same deep breath would kill you instantly. Earth's first atmosphere, if you can call it that, was mostly hydrogen and helium, the lightest elements, probably captured from the solar nebula during the planet's formation. But Earth's gravity wasn't strong enough to hold these light gases against the heat of the early sun and the violence of the moon-forming impact. They escaped into space, leaving Earth with essentially no atmosphere at all immediately after that impact. The second atmosphere formed through a process called outgassing. As Earth's interior heated up and partially melted, volatiles, gases that had been trapped in minerals, were released and rose to the surface through volcanic eruptions. This early atmosphere was dominated by water vapor, carbon dioxide, nitrogen, and smaller amounts of methane, ammonia, and sulfur compounds. There was virtually no free oxygen. In fact, any oxygen that did appear quickly reacted with iron and other reduced elements in the crust and mantle, preventing it from accumulating in the atmosphere. As Earth cooled, the water vapor condensed and fell as rain, enormous rains that may have continued for thousands or even millions of years, gradually filling the ocean basins. This left an atmosphere primarily of carbon dioxide and nitrogen, probably with a surface pressure several times higher than today. The young Earth would have had a strong greenhouse effect from all that carbon dioxide, helping to keep the surface warm despite the sun being about 30% dimmer than it is today. A paradox that puzzled scientists until they realized how different the atmosphere must have been. For the first 2 billion years of Earth's history, the atmosphere remained essentially oxygen-free. This created a very different world, Without oxygen, there was no ozone layer, so ultraviolet radiation from the sun penetrated all the way to the surface, likely limiting any early life to protected environments underwater or underground. The rocks at the surface contained abundant iron in its reduced form, which oxidizes readily today but remained stable in that oxygen-poor environment. The sky was probably orange or reddish, lacking the blue color created when oxygen molecules scatter sunlight. Then, around 3.5 billion years ago, something remarkable happened. Life evolved photosynthesis. Tiny, single-celled organisms called cyanobacteria, essentially ancient versions of modern blue-green algae, developed the ability to use energy from sunlight to split water molecules, using the hydrogen to build organic compounds and releasing oxygen as waste. This was a chemical trick of extraordinary sophistication, but initially it didn't change the atmosphere much because all that oxygen was immediately consumed, reacting with dissolved iron in the ocean and with rocks at the surface. For nearly 1 billion years, the oxygen produced by photosynthesis was soaked up by Earth's iron-rich rocks and oceans. Evidence of this is preserved in geological formations called banded iron formations. Alternating layers of iron-rich and iron-poor rock that formed when oxygen from cyanobacteria oxidized dissolved iron in seawater, causing it to precipitate and sink to the ocean floor. These formations, found on every continent, represent an enormous sink of oxygen, all the molecular oxygen that was produced but didn't make it into the atmosphere during this long period of waiting. Around 2.4 billion years ago, something changed. This is called the Great Oxidation Event, and it marks one of the most important transitions in Earth's history. Over a relatively short period, perhaps just a few 100 million years, atmospheric oxygen levels rose from less than 1 part per million to perhaps 1%, possibly higher. This might not sound dramatic, but it was enough to fundamentally transform the planet. What caused the Great Oxidation Event? For a long time, scientists assumed it was simply that photosynthetic organisms had finally produced enough oxygen to overwhelm all the sinks, that all the iron had finally been oxidized and oxygen had nowhere to go but the atmosphere. But recent research suggests a more complex story, one intimately tied to plate tectonics. Around the time of the Great Oxidation Event, the composition of Earth's continental crust underwent a significant change. Earlier crust was rich in a mineral called olivine, which reacts readily with water in a process that consumes oxygen. But around 2.5 billion years ago, perhaps related to the onset or intensification of modern-style plate tectonics, the composition shifted toward more quartz-rich rocks that don't consume oxygen as readily. This change in crustal composition reduced the oxygen sink, allowing oxygen to accumulate. At the same time, plate tectonics itself may have played a more direct role. When plate tectonics initiated or became more vigorous, it began stirring the entire mantle more effectively, bringing oxidized material from deep within Earth to the surface through volcanism. Remember that during Earth's formation, when heavy metals sank to form the core, they left behind oxygen in certain minerals in the mantle. This oxygen had remained locked away in the deep interior for billions of years. But when deep subduction and mantle convection began mixing the mantle thoroughly, This oxidized material reached the surface, releasing oxygen into the atmosphere and oceans. The Great Oxidation Event was catastrophic for existing life. Oxygen is highly reactive, toxic to organisms that evolved in its absence. This period may have seen the first great mass extinction, sometimes called the oxygen catastrophe, as organisms that couldn't tolerate oxygen were wiped out or driven into oxygen-free refuges where they persist even today as anaerobic bacteria. But for organisms that could tolerate oxygen, or, better yet, use it for metabolism, this new atmosphere opened extraordinary opportunities. Aerobic respiration, using oxygen to burn organic molecules, yields far more energy than anaerobic metabolism. This energy surplus would eventually enable the evolution of larger, more complex organisms. The Great Oxidation Event had other profound effects. The oxygen reacted with methane in the atmosphere, a much stronger greenhouse gas than carbon dioxide, breaking it down. This may have triggered a series of severe glaciations, called snowball Earth events, where much or all of the planet's surface froze. The oxygen also formed ozone in the upper atmosphere, creating a protective layers that absorbed ultraviolet radiation, making the surface much safer for life. But oxygen levels didn't immediately rise to modern values. After the initial surge to around 1%, oxygen levels appear to have plateaued for another billion years or more, in a period sometimes called the boring billion, when environmental conditions remained relatively stable and evolutionary innovation seems to have slowed. It wasn't until the Neoproterozoic era, between about 1 billion and 540 million years ago, that oxygen levels rose again in what's called the Neoproterozoic oxygenation event. This second rise in oxygen was also linked to plate tectonics and continental evolution. As continents grew larger through the accumulation and collision of smaller land masses, weathering increased. Continental rocks weather more effectively than oceanic crust in removing carbon dioxide from the atmosphere because they're exposed to fresh waters and to plants once they evolved. This weathering releases phosphorus and other nutrients that feed phototrophic organisms in the ocean, increasing oxygen production. Meanwhile, the carbon that's been locked away in organic matter and carbonate rocks represents oxygen that isn't consumed in decay, allowing it to accumulate in the atmosphere. By the end of the Neoproterozoic, oxygen levels had risen to perhaps 10 to 20% of the atmosphere, approaching modern levels. This set the stage for the Cambrian explosion, the sudden diversification of complex life forms about 540 million years ago. Animals require high oxygen levels because they're active and have high metabolic rates. The rise in oxygen literally made animals possible. The story of Earth's atmosphere is a story of co-evolution between geology, chemistry, and biology. Plate tectonics provided the mechanism for recycling elements and maintaining climate stability. Life provided the oxygen, and the oxygen in turn enabled more complex life, which altered the atmosphere further, creating the breathable air we depend on. It's a reminder that Earth's habitability isn't just about being the right distance from the sun. It's about having the right interior dynamics, the right geological processes, the right feedbacks between the living and non-living components of the planet. Earth isn't habitable by accident. It's habitable because its geology and biology work together in ways that maintain habitable conditions: water world, oceans, and hydrosphere. Water is the most distinctive feature of Earth. From space, it's what makes our planet blue, covering about 71% of the surface, a global ocean with an average depth of over 2 miles, containing about 326 million cubic miles of water. But Earth's water isn't just in the oceans. It's in the atmosphere as vapor and clouds. It's frozen in ice caps and glaciers, containing about 2% of Earth's water, but 70% of its fresh water. It's underground in aquifers and in soil moisture. It's in living things, since most organisms are mostly water. It flows in rivers and fills lakes. It's everywhere, constantly moving through what we call the hydrological cycle, evaporating, condensing, precipitating, flowing, in an endless circulation that has been running for billions of years. Where did all this water come from? That's been a subject of debate among scientists. Earth formed in the inner solar system where temperatures were high enough that most water would have evaporated during the planet's formation. Yet Earth obviously has abundant water, far more than Venus or Mars. There are two main sources that probably both contributed. First, even in the warm inner solar system, some minerals can trap water in their crystal structures, incorporating it chemically. When these minerals were cooked in Earth's interior and melted, they released their water, which then rose to the surface through volcanism, a process called outgassing that continues today. Second, water was delivered from the outer solar system by comets and water-rich asteroids that formed farther from the Sun where ice was stable. During the late heavy bombardment, countless impacts delivered water to Earth's surface. Recent research comparing the isotopic composition of water in comets, asteroids, and Earth's oceans suggests that asteroids, particularly those from the outer asteroid belt, were the dominant source, though comets contributed as well. Once on Earth, water accumulated in the lowest areas, forming the first oceans. Those early oceans were very different from modern ones. They were probably warmer, perhaps 40 to 80 degrees Celsius on average, heated by a younger, more active Earth with more internal warmth and more volcanic activity. They were more acidic, with a pH perhaps as low as 5 or 6 compared to today's slightly basic 8.1, due to high concentrations of dissolved carbon dioxide from volcanism. They contained different dissolved minerals, particularly high concentrations of iron in its reduced form, which would give the water a greenish tint. When photosynthesis evolved and began producing oxygen, this dissolved iron oxidized and precipitated out, forming those banded iron formations we discussed earlier and gradually changing the ocean's chemistry. The oceans play a crucial role in Earth's climate system. Water has an extremely high heat capacity, meaning it takes a lot of energy to change its temperature. The oceans store enormous amounts of heat, absorbing solar energy during the day and summer, releasing it at night and in winter, buffering temperature extremes. Ocean currents transport heat around the planet, warming high latitudes and cooling the tropics. The Gulf Stream, for instance, carries warm water from the Caribbean northward, along the eastern coast of North America and then across the Atlantic toward Europe, making Western Europe much warmer than other regions at similar latitudes. Without the Gulf Stream, Britain would have a climate more like Newfoundland. The oceans also regulate atmospheric carbon dioxide through several mechanisms. Carbon dioxide dissolves readily in seawater, forming carbonic acid, which then dissociates into bicarbonate and carbonate ions. These ions are used by marine organisms to build shells and skeletons of calcium carbonate. When these organisms die, many of their shells sink to the seafloor, locking carbon away in limestone. This biological pump removes enormous quantities of carbon from the atmosphere-ocean system, storing it in rocks that may eventually subduct and melt, returning carbon dioxide to the atmosphere through volcanism millions of years later. Water is essential for plate tectonics. When oceanic crust forms at mid-ocean ridges, it's hot and dry. But as it spreads away from the ridge and cools, water from the ocean percolates into cracks and pores in the rock, chemically altering the minerals, a process called hydrothermal alteration. This water, bound in minerals, travels with the plate until it subducts. As the descending plate heats up in the mantle, the water is released, lowering the melting point of the overlying mantle and causing it to partially melt. Without water, subduction wouldn't generate the volcanism that builds island arcs and continental crust. The water that emerges from those volcanoes eventually returns to the ocean through rain, completing a cycle that has been running throughout Earth's history. Water is also, of course, essential for life as we know it. It's the universal solvent, able to dissolve more substances than any other liquid, making it perfect for transporting nutrients and waste in living cells. It has unusual properties, expanding when it freezes, which makes ice float, insulating liquid water below, and preventing oceans from freezing solid from the bottom up. It's transparent to visible light, allowing photosynthesis to occur in the upper layers of the ocean. Life on Earth originated in water, probably in the oceans, and remained exclusively aquatic for most of Earth's history. Only in the last 500 million years or so did life successfully colonize land, and even terrestrial life remains dependent on water, carrying a miniature ocean within every cell. The hydrological cycle, the movement of water through Earth's systems, is driven by solar energy. The sun heats the ocean surface, causing water to evaporate. This water vapor rises into the atmosphere, where it cools and condenses into clouds. Eventually, it falls as precipitation, rain or snow, returning to the surface. Some runs off immediately into streams and rivers, flowing back to the ocean. Some infiltrates into the ground, recharging aquifers or emerging later as springs. Some is taken up by plants and later released through transpiration. The entire cycle, from ocean to atmosphere to land and back to ocean, takes on average about 9 days for atmospheric water. But water in ice caps might be frozen for thousands of years, and water in deep aquifers might be isolated from the surface cycle for millions of years. This moving water shapes the land. Rivers carve valleys, transport sediment, and deposit it in deltas and floodplains. Glaciers gouge out fjords and leave behind distinctive landforms. Waves erode coastlines. Rain weathers rocks, breaking them down chemically and physically. Over millions of years, water has been one of the primary sculptors of Earth's surface, wearing down mountains, filling basins, constantly moving material from high elevations to low, from land to sea. And so Earth's water, cycling endlessly, connecting atmosphere to ocean to land, driving weather and climate, enabling plate tectonics, supporting all life, is not just a feature of our planet. It's a defining characteristic, the element that makes Earth truly unique in the solar system, a world not just of rock and metal, but of water in all its forms, liquid and solid and vapor, in constant motion, bringing change and possibility wherever it flows. The spark of life. At some point in Earth's first billion years, somewhere in the vast oceans or perhaps in a hydrothermal vent or a shallow tidal pool, chemistry became biology. Non-living molecules organized themselves into systems that could metabolize, that could reproduce, that could evolve. This transition, from chemistry to life, is one of the deepest mysteries in science. We don't know exactly when it happened, though chemical signatures in ancient rocks suggest life may have existed by 3.8 billion years ago, possibly earlier. We don't know exactly where it happened, though several promising locations have been proposed. And we certainly don't know exactly how it happened, though researchers have proposed many mechanisms. What we do know is that it happened, and that once it did, life fundamentally changed Earth. The oldest direct evidence of life comes from structures called stromatolites, layered mounds built by communities of microorganisms, particularly cyanobacteria. Modern stromatolites still grow in a few places, like Shark Bay in Australia, where high salinity keeps away organisms that would otherwise eat the bacteria. Ancient stromatolites, remarkably similar to modern ones, have been found in rocks as old as 3.5 billion years. Even older evidence comes from chemical signatures, particular ratios of carbon isotopes that suggest biological processing, found in rocks up to 3.8 billion years old or possibly older. The first life forms were almost certainly single-celled and relatively simple by modern standards, though even the simplest cell is extraordinarily complex from a chemical standpoint. They probably lived in water, protected from ultraviolet radiation that bathed the surface in the absence of an ozone layer. They obtained energy and nutrients from their environment, perhaps using chemical reactions similar to modern bacteria that live around hydrothermal vents, oxidizing hydrogen or iron or sulfur compounds for energy. These chemosynthetic organisms didn't need sunlight, just the right chemistry, and hydrothermal vents would have provided abundant chemical energy on the early Earth. The evolution of photosynthesis, probably around 3.5 billion years ago, was revolutionary. Photosynthesis allowed organisms to use sunlight, an essentially unlimited energy source, to build organic molecules from carbon dioxide and water. Early photosynthesis probably didn't produce oxygen, instead using hydrogen sulfide or other compounds as the electron source. But eventually, some cyanobacteria evolved oxygenic photosynthesis, splitting water molecules and releasing oxygen as waste. This opened up a vast new energy source, and, as we've discussed, eventually transformed Earth's atmosphere, though that took over 1 billion years. For most of Earth's history, from about 4 billion years ago until about 2 billion years ago, life consisted entirely of prokaryotes, cells without nuclei, essentially bacteria and archaea. These organisms seem simple, but they were incredibly successful, diversifying to fill every conceivable niche where liquid water existed and where chemistry could provide energy. They evolved complex metabolisms, sophisticated genetic systems, and even forms of cooperation and communication. Around 2 billion years ago, one of the most important events in the history of life occurred: the evolution of eukaryotes, cells with nuclei and other complex internal structures. This probably happened through a process called endosymbiosis, where one cell engulfed another but didn't digest it. Instead, the engulfed cell continued living inside the host, eventually becoming an organelle. Mitochondria, the power plants of eukaryotic cells, were probably once free-living bacteria that were engulfed by an early eukaryote. Chloroplasts, which perform photosynthesis in plants and algae, were probably once free-living cyanobacteria. The evidence for endosymbiosis is strong. Both mitochondria and chloroplasts have their own DNA, separate from the cell's nuclear DNA, and this DNA is most similar to bacterial DNA. Eukaryotes remained single-celled for another billion years, but they developed increasing complexity. Sexual reproduction evolved, allowing genetic material from two individuals to combine, greatly increasing genetic diversity and accelerating evolution. Some eukaryotes developed the ability to form temporary colonies or even primitive multicellular structures. Around 600 million years ago, after the Neoproterozoic oxygenation event raised oxygen levels, truly complex multicellular life evolved. The Ediacaran biota, strange soft-bodied organisms preserved in rocks around the world, represent some of the earliest experiments with multicellularity. Many of these organisms look unlike anything alive today, with body plans that were never repeated, evolutionary experiments that didn't survive into later periods. Then, about 540 million years ago, Earth experienced what's called the Cambrian explosion, though explosion is a geological term meaning it happened over about 20 million years. Suddenly, or at least suddenly in geological terms, most of the major animal body plans appeared in the fossil record. Animals with shells, with skeletons, with segmented bodies, with complex eyes, with jointed legs, all appeared within a relatively short time. The trigger for this explosion is still debated, but rising oxygen levels, the evolution of predation creating an evolutionary arms race, and possibly environmental changes, including plate tectonic reorganization and climate shifts, all likely played roles. Life's subsequent history has been one of diversification and innovation, but also of repeated catastrophe. Earth has experienced at least 5 major mass extinctions and numerous smaller ones. The most severe was the Permian-Triassic extinction about 252 million years ago, which killed perhaps 95% of all marine species and 70% of terrestrial vertebrate species. The cause is still debated, but probably involved massive volcanism in Siberia, releasing enormous quantities of carbon dioxide and other gases, causing severe global warming and ocean acidification. The most famous extinction is the Cretaceous-Paleogene event 66 million years ago, which killed the non-avian dinosaurs and about 75% of all species. This was caused by the impact of an asteroid about 6 miles in diameter near what's now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs, created tsunamis hundreds of feet tall, ignited wildfires across continents, and threw enough dust into the atmosphere to block sunlight for months or years, collapsing food chains worldwide. Yet life recovered from every extinction, though recovery sometimes took millions of years. And each recovery saw innovations, new groups of organisms filling niches left vacant by the extinct. After the Permian-Triassic extinction, dinosaurs rose to dominate terrestrial ecosystems. After the Cretaceous-Paleogene extinction, mammals, which had existed but remained small for over 150 million years, rapidly diversified and grew larger, eventually giving rise to primates, and ultimately to us. The story of life on Earth is a story of resilience, of adaptation, of evolution finding solutions to challenges. But it's also a reminder that life didn't evolve in isolation from geology. The availability of oxygen, determined by geological processes, enabled complex life. The movement of continents, driven by plate tectonics, created new habitats and drove evolution. Volcanic activity and asteroid impacts caused extinctions, but also created opportunities. Earth's life and Earth's geology are inseparable, co-evolving, each shaping the other in an intricate dance that has continued for billions of years. Climate through time. If you think Earth's climate is changeable now, consider this. At various times in Earth's past, palm trees have grown near the poles, and ice has extended almost to the equator. The entire planet has been warmer than today for most of its history, yet it has also experienced periods of such extreme cold that it may have frozen completely. Understanding Earth's climate history isn't just interesting in its own right. It helps us understand what controls climate, what feedbacks exist, and how resilient the Earth system is to perturbation. Climate is controlled by several factors, starting with the energy input from the sun. The young sun was dimmer than today, about 30% less luminous 4 billion years ago, gradually brightening as its fusion reactions intensified. According to simple calculations, this dim young sun should have left Earth frozen solid. Yet we know Earth had liquid oceans throughout most of its history. This is called the faint young sun paradox. The solution is that Earth's early atmosphere contained much higher concentrations of greenhouse gases, particularly carbon dioxide and possibly methane, which trapped enough heat to keep the surface warm despite the dim sun. As life evolved and began removing carbon dioxide from the atmosphere, and as the continents grew and weathering increased, carbon dioxide levels gradually declined. But the sun was brightening, so the two effects largely balanced each other out, maintaining temperatures suitable for liquid water through an impressive feat of planetary self-regulation via the carbon cycle we discussed earlier. But this regulation wasn't perfect. Several times in Earth's history, the climate system tipped into an extreme cold state called Snowball Earth. The best documented Snowball Earth episodes occurred during the Cryogenian period, between about 720 and 635 million years ago, part of the Neoproterozoic era. During these events, glaciers may have extended all the way to the equator, and the oceans may have frozen over entirely or nearly so, with only some open water remaining near volcanic islands or at the equator. How does a planet freeze completely? The process probably started with normal glaciation, perhaps triggered by a particularly large continent positioned near the equator where weathering rates are highest, pulling down atmospheric carbon dioxide. Once ice and snow begin to spread toward lower latitudes, they increase Earth's albedo, its reflectiveness. Ice reflects most sunlight back to space instead of absorbing it, so temperatures drop further. Ice spreads farther, a runaway positive feedback that doesn't stop until the entire planet is frozen. You might wonder how Earth escaped from this frozen state. The answer is volcanic activity. Even with the surface frozen, volcanism would have continued, driven by internal heat from radioactive decay. With no liquid water to weather rocks and no photosynthesis to remove carbon dioxide. Volcanic carbon dioxide would have accumulated in the atmosphere over millions of years. Eventually, after perhaps 10 or 20 million years, the greenhouse effect would have become strong enough to start melting the ice. Once melting began, the process reversed. Less ice meant less reflection, more absorption of sunlight, more warming, more melting, another runaway feedback, this time toward warmth, melting the ice caps in perhaps just a few centuries. The aftermath of Snowball Earth episodes would have been dramatic. The ice, when it melted, left behind distinctive deposits, glacial sediments at all latitudes, often topped by carbonate rocks that formed in the super-greenhouse conditions following the thaw. Life survived these frozen episodes, probably in refuges where liquid water persisted, perhaps in volcanic hot springs or in the deep ocean where geothermal heat kept water liquid. When the ice melted, life diversified dramatically, possibly because the extreme conditions selected for adaptability, and because new habitats opened up. The Phanerozoic Eon, from 540 million years ago to the present, has seen milder climate variations than Snowball Earth, but still dramatic by human standards. During the Carboniferous period, about 360 to 300 million years ago, vast swamp forests covered much of the continents. These forests removed enormous amounts of carbon dioxide from the atmosphere and buried it as organic matter that eventually became coal deposits. The reduction in greenhouse gases, combined with the arrangement of continents that promoted ice accumulation, triggered the Karoo Ice Age, the most recent major glaciation before the current ice age. Yes, we're currently in an ice age, called the Quaternary glaciation, which began about 2.6 million years ago and continues today. We happen to be living in an interglacial period, a relatively warm interval between glacial maxima. During glacial maxima, which occurred most recently about 20,000 years ago, ice sheets covered much of North America and Northern Europe. Sea level was about 400 feet lower than today, and global temperatures were about 8 to 10 degrees Celsius cooler on average. These glacial cycles are driven by variations in Earth's orbit and axial tilt, called Milankovitch cycles, which change how much solar energy reaches different parts of Earth's surface at different times of year. These orbital variations don't change the total amount of solar energy Earth receives by much, but they change its distribution, and that's enough to trigger feedbacks that amplify the effect. Between major glaciations, Earth has experienced greenhouse periods when it was much warmer than today. During the Cretaceous period, from about 145 to 66 million years ago, global temperatures were perhaps 8 to 15 degrees Celsius warmer than today. There was no ice at either pole. Sea level was much higher, flooding large areas of the continents. Dinosaurs roamed forests in what's now Alaska, and crocodile-like reptiles swam in seas that covered much of what's now the Great Plains. The warmth was driven by high atmospheric carbon dioxide, possibly 4 to 6 times modern pre-industrial levels, released by intense volcanic activity as the supercontinent Pangaea broke apart and new ocean basins formed. Climate affects life profoundly. The positions of climatic zones determine where different ecosystems can exist. Deserts form where descending air creates high pressure and dry conditions. Rainforests thrive where warm, moist air rises and cools, dropping abundant rain. Climate changes, when they happen faster than organisms can adapt or migrate, cause extinctions. But climate changes also create opportunities, opening new habitats, creating selection pressures that drive evolution. Understanding past climates gives us context for current changes. Earth's climate has changed dramatically over geological time, driven by changes in solar output, in atmospheric composition, in continental positions, in ocean currents, in life itself. The current warming, driven by human emissions of greenhouse gases, is happening at a rate that's fast, even by the standards of some past climate changes, faster than many ecosystems can adapt. But Earth has been warmer before, and colder before, and life has persisted through all Vaniha, it. The planet will survive. The question is, what changes will occur to ecosystems and to human civilization during the transition to whatever new equilibrium climate state we're creating? Earth today and tomorrow. Here we are, standing on a planet 4.54 billion years old, looking around at mountains and oceans and forests and deserts, at a world that seems solid and permanent, but that is, in fact, constantly changing. Right now, as you rest and listen, continents are drifting, oceans are spreading, mountains are rising and eroding, volcanoes are building and erupting, earthquakes are rupturing, the magnetic field is fluctuating, the atmosphere is circulating, water is cycling, and life is evolving. All of it happening too slowly for us to perceive directly, yet cumulatively shaping Earth's surface and environment in ways that would be dramatic if we could watch them in time-lapse. The Atlantic Ocean is growing wider by about an inch per year as seafloor spreading continues at the mid-Atlantic ridge, pushing the Americas away from Europe and Africa. The Pacific Ocean is shrinking at about 3 inches per year as subduction consumes oceanic crust faster than it's created, and the Pacific Plate and other plates carrying continents are slowly closing this ancient ocean. In perhaps 200 million years, if current trends continue, the Atlantic may begin to close, and the continents may reassemble into a new supercontinent, continuing the cycle that has seen continents gather together and break apart several times in Earth's history. The Himalayas continue rising as India pushes into Asia, though erosion removes rock as fast as or faster than it's uplifted, keeping the mountains in a kind of steady state. The East African Rift is actively splitting the African continent, forming a new ocean basin that, in 10 or 20 million years, may separate the Horn of Africa from the rest of the continent as the Red Sea and Gulf of Aden have already separated the Arabian Peninsula. Iceland is growing larger as the mid-Atlantic ridge emerges above sea level there, adding new land through volcanic eruptions. The Hawaiian Islands are slowly drifting northwest, carried on the Pacific Plate, while new islands form over the hotspot that currently feeds the Big Island's active volcanoes. Yellowstone's supervolcano continues to slumber, fed by a deep mantle plume, having last erupted about 640,000 years ago, and statistically due for another eruption sometime in the next few 100,000 years, though predicting exactly when is impossible. The magnetic field continues to weaken gradually, as it has been doing for the past 2,000 years, possibly heading toward another magnetic reversal like those that have occurred at hundreds of times throughout Earth's history. These reversals happen irregularly, on average every few 100,000 years, though the last one was 780,000 years ago, making us perhaps overdue. During a reversal, which takes a few thousand years to complete, the magnetic field doesn't disappear but becomes more complex, with multiple magnetic poles wandering around the surface before settling into new positions with the polarity reversed. Life survives these reversals, though increased exposure to cosmic radiation and solar particles during the transition period may have biological effects. Earth's atmosphere continues to change. The natural carbon cycle continues, though human activities have perturbed it significantly. Since the Industrial Revolution, humans have released billions of tons of carbon dioxide, primarily by burning fossil fuels, ancient organic matter stored underground for hundreds of millions of years. This has raised atmospheric carbon dioxide from about 280 parts per million to over 400 parts per million, higher than any time in at least the last few million years, possibly much longer. The enhanced greenhouse effect is warming the planet, melting ice caps, raising sea level, changing precipitation patterns, and stressing ecosystems. The rate of change is fast enough that it's difficult for many species to adapt or migrate, leading to predictions of significant biodiversity loss. Yet Earth has seen higher carbon dioxide levels before, much higher. During the Eocene epoch, about 50 million years ago, levels may have exceeded 1,000 parts per million, and global temperatures were much warmer. The difference is that previous changes generally occurred over millions of years, allowing life and ecosystems time to adapt. The current change is happening over decades and centuries, faster than many organisms can evolve or migrate. This doesn't mean Earth can't handle it. Earth will be fine, but ecosystems will change. Some species will go extinct, others will thrive, and the resulting world may look quite different from the one we know. humans have become a geological force. We move more sediment through construction and agriculture than all the world's rivers combined. We've altered the composition of the atmosphere. We've changed the chemistry of the oceans. We've driven some species extinct and spread others worldwide. We've synthesized materials that never existed naturally. Some scientists argue that we've entered a new geological epoch called the Anthropocene, defined by the global impact of human activities. Whether future geologists, billions of years from now, if such exist, will be able to detect a distinctive Anthropocene layer in the rock record remains to be seen. But they might notice extinction pulses, changes in atmospheric composition recorded in ice cores or fossil soils, the sudden global spread of certain species, or deposits of unusual materials like concrete and plastics. Looking forward, what does Earth's future hold? On timescales of millions of years, plate tectonics will continue reshaping continents and oceans. Life will continue evolving, adapting to changing conditions. The sun will continue brightening by about 10% per billion years, gradually increasing the energy Earth receives. This will eventually make Earth too warm for comfort, though the carbon cycle should compensate by drawing down atmospheric carbon dioxide as weathering increases with higher temperatures. But this can only continue as long as there's carbon dioxide to remove. Eventually, perhaps a billion years from now, carbon dioxide levels may drop so low that photosynthesis becomes difficult or impossible. Without photosynthesis, the base of most food chains collapses. On even longer timescales, 2 to 3 billion years from now, the sun will be so luminous that Earth's surface temperature will rise dramatically. The oceans will begin to evaporate. Water vapor is a greenhouse gas, so this will create a runaway greenhouse effect, evaporating more water, warming the planet further, eventually leaving the Earth as hot and dry as Venus is today, with a thick atmosphere of steam and carbon dioxide and surface temperatures hot enough to melt lead. Life on the surface will be impossible, but that's billions of years away. For now, for the foreseeable human future, Earth remains habitable, resilient, dynamic. It survived asteroid impacts, supervolcano eruptions, extreme climate swings, mass extinctions. It's a robust system with powerful negative feedbacks that tend to maintain habitable conditions. The plate tectonic thermostat will keep working as long as the interior remains hot enough to drive convection. The water cycle will continue distributing moisture. Life will continue adapting to whatever conditions prevail. Earth isn't fragile in the sense of being easily destroyed. Earth has been through far worse than anything humans can do to it. But Earth's current climate state, the particular distribution of ecosystems and species that exists now, is more fragile. Those can change rapidly. From Earth's perspective, these changes are just another chapter in a long story. From the perspective of current life, including us, the changes matter a great deal. The question isn't whether Earth will survive. Of course it will. The question is what will survive on it, and what the world will look like when the current period of rapid change settles into a new equilibrium. Closing reflection. And so we reach the end of our journey, though of course Earth's journey continues. We've traveled 4.5 billion years, from a cloud of dust to a living world, from fire to water, from chaos to complexity. We've watched continents form and drift, oceans fill and freeze, atmospheres transform, life arise and diversify. We've seen how geology and biology are intertwined, each shaping the other, neither making sense without the other. You are lying here tonight on a planet that is, in the truest sense, alive. Not in the way an organism is alive, but alive with motion, with change, with cycles and flows and transformations. Beneath you, the mantle churns slowly, convecting over millions of years, driving the plates that carry continents across the surface. Deep below, a liquid iron sea swirls, generating the magnetic field that shields you from the solar wind. Above, the atmosphere circulates, carrying water and heat, clouds forming and dissolving, winds blowing, storms gathering and breaking. Water moves through the soil beneath you, through the air above, through every living thing. The same water molecules that filled the first oceans, that nurtured the first life, that have cycled through countless organisms and environments. The atoms in your body have their own deep history. The oxygen you breathe was exhaled by plants and algae, but before that, it was locked in water molecules split by photosynthesis. And before that, it was in minerals in rock. And before that, it formed in the heart of stars that died before our solar system existed. The carbon in your cells has cycled through the Earth system many times, and carbon dioxide in the atmosphere, dissolved in the ocean, locked in limestone, released by volcanoes, taken up by plants, eaten by animals, released as waste, dissolved again. The calcium in your bones may once have been in shells of ancient sea creatures compressed into limestone, subducted into the mantle, melted, erupted in a volcano, weathered from rock, dissolved in groundwater, absorbed by another living thing over and over. You are made of earth, literally, fashioned from its elements, sustained by its cycles, and earth is made of stardust, assembled from the debris of stellar explosions, carrying the heavy elements forged in the hearts of stars and supernovas. We are, all of us, connected to the deepest history of the cosmos, part of an unbroken chain that stretches from the Big Bang through stellar nucleosynthesis, through the formation of planets, through the evolution of life, to this moment, to you, resting here, listening, thinking, being. This perspective, this deep time view, can be humbling. We live such short lives, just decades in a story that spans billions of years. We occupy such a small space, a few miles of atmosphere and a thin crustal layer on one small planet. And yet we're part of something vast, something ancient, something still unfolding. The story of Earth is not finished. What comes next depends partly on chance, the random impacts and volcanic eruptions and evolutionary innovations that have always shaped history. But it also depends, for the first time, on choice, on decisions made by a species that has become self-aware, that has learned to read the rocks and reconstruct the past, that has developed the power to change the planet's environment. We are living through a unique moment in Earth's history, a time when the planet's dominant species is aware of its effects, can predict their consequences, and can choose, to some extent, what kind of world to create. It's a responsibility that our planet's previous inhabitants never had to bear. It's both terrifying and inspiring. But tonight, let those thoughts rest. You've journeyed far tonight through space and time. You've seen Earth born in fire, watched it cool and come alive, followed its transformation from hellscape to paradise. You've seen how geology creates conditions for life, how life transforms geology, how the two dance together across the ages. Rest now in the knowledge that you live on a remarkable world, a planet that has been many things and will be many more, a planet that carries in its rocks and atmosphere and living things a memory of 4 billion years of history. The ground beneath you is ancient. The air around you has been renewed countless times. The water you drink has been cycling since the first oceans formed. You are part of it all, a brief arrangement of atoms that is, for this moment, conscious, aware, alive, able to wonder at the vast story you are part of. If you're still awake and you've enjoyed this journey through deep time, through Earth's extraordinary history, consider liking this video and subscribing to the Sleepy Science Society. There are more cosmic journeys ahead, more stories of the universe to explore together. But for now, sleep well, dream softly, and know that even as you rest, Earth turns on beneath you, unchanged yet ever-changing, ancient yet new, your home in the cosmos and the home of everything you've ever known. Good night.